Roughly 1 century ago, physicists discovered that our intuitive understanding of the world is merely an approximation, a limiting case of a strange mechanism that challenges our most basic conception of logic. Quantum theory has been incredibly successful in describing nature, but it does so in a way that fundamentally differs from our everyday experience. Due to this unsettling discrepancy, quantum physics is frequently picked up by movies and literature, though often in a very distorted way. This video aims to convey maybe the most pivotal concept of quantum mechanics using simple pictures and animations that still accurately represent the underlying formalism. I'll further try to mention some open research topics. To do this, let's consider perhaps the most prominent protagonist of quantum physics, the electron. As a starting point, one can imagine electrons as tiny particles that revolve around the core of atoms. And while the idea of electrons as tiny balls has its problems, as we'll soon see, it is true to the extent that when directed onto a special screen, they leave behind little dots, reminiscent of shooting tiny ping pong balls onto a sticky wall. Let's stick to the ping pong ball analogy for a moment. Imagine randomly shooting them onto the wall while obstructing their path with a barrier that has 2 openings. Then we create sort of a negative image of that barrier on the wall. This property distinguishes ping pong balls fundamentally from, for example, sound waves. You see, waves, whether they are water, sound, or of mechanical nature, all spread out again after squeezing through an opening. Furthermore, waves exhibit a phenomena called interference, where 2 overlapping waves either interfere constructively to create a single more powerful wave, or destructively when their peaks are out of phase, causing them to cancel each other out. This effect makes technologies like noise-cancelling headphones possible. Now, these 2 properties combined imply that a wave traveling through the double-slit barrier from before first splits into 2 smaller waves, which then interfere, causing them to enhance each other in some regions and cancel out in others. On a detector, we might then see dark areas where the waves interfered constructively and empty spots where they interfered destructively. Now, let us turn back to the electrons. What happens if we force them through this arrangement? When we conduct the experiment shooting electrons one after another through the double slit, we initially observe the familiar dots on the detector screen, though we soon realize that they appear in places which the ping pong balls could never reach. And then, over time, we see an interference pattern emerging. Just as in the case of waves, there are untouched regions indicating destructive interference and especially densely hit regions of constructive interference. This effect, where quantum objects display features from both waves and particles, remained unexplainable, until a French plus a group of German physicists came up with an absurd solution. Their idea was that rather than selecting the upper or lower slit, the electron could actually go through both slits at the same time. In fact, they modeled the electron as a non-local entity, able to take all possible trajectories simultaneously, a state termed superposition. These trajectories can now also interfere with one another. So, in a way, they allowed the electron to interfere with different evolutions of itself. Mathematically, they derived the electron's dynamic by combining all the possible ways in which it could move as a particle into a wave evolution. The idea went fully against the prevailing worldview of physicists at the time, and there was a general expectation that it would soon be falsified by other observations. But that never happened. In fact, every subsequent experiment, and there has been an uncountable variety of them, followed the prediction of this seemingly implausible concept. This was the birth of quantum mechanics, nowadays considered one of the most fundamental and rigorously tested theories we have. Yet, despite their success in predicting experimental outcomes, these early quantum physicists faced a central issue. Namely, while describing quantum states as superpositions of different possibilities works mathematically, any measurement would reveal just one precisely localized impact zone. Furthermore, any attempt to actively monitor the electron's movement, for example by scattering light of it before it goes through the slits, removed the interference effect and the electron behaved more like a tiny ball again. In other words, as soon as someone actually measured the system, the peculiar quantum dynamics just disappeared. Now, our quantum pioneers did come up with a rule that was able to assign probabilities to different measurement outcomes based on their wave of possibilities concept. Once again, their proposal was in perfect agreement with experimental results. Yet it itself came with two problems. The first was that it implied a probabilistic nature of measurement results not stemming from a lack of information, but as an intrinsic property. So unlike a coin flip where, with perfect knowledge of the throw and air resistance, one can always predict the outcome, quantum theory suggests that a process could remain fundamentally indeterministic. This was a thorn in the side of many physicists, and most famously Albert Einstein. It was only recently that physicists were able to prove that while the average result over many iterations can be well known, the outcome of each individual experiment really is impossible to predict. The second issue with the rule was that it didn't nicely connect to the rest of the theory. Quantum mechanics seemed to be divided into two stages, one prior to any measurement, with weird superpositions and interference effects, and one afterwards where all these things suddenly vanished, a paradox known as the measurement problem. Since then, there has also been progress in this regard, most notably the introduction of the decoherence mechanism in the 1970s, which describes how the relations of various overlapping evolutions of a quantum object get distorted through interaction with their surroundings. And since waves with a mushed-up phase relation show no interference, the strange quantum dynamics disappears in any normal environment. This also explains the absence of superpositions on our scale, where everything constantly interacts with everything else. Nonetheless, the measurement problem persists, as decoherence still doesn't explain why the many superimposed branches of a quantum state turn into a single measurement outcome, and how this outcome is selected. This question is extremely difficult to pin down experimentally, and thus remains an open playground for the more philosophical interpretations of quantum mechanics, including the many worlds theory frequently picked up in pop culture. So while there are still open questions, and admittedly all of this is unintuitive, it is crucial to highlight that precisely this idea that a state has to be understood as a mixture of all its possible dynamics has enabled physicists to predict experimental results with up to 15 digits measurement agreement, making quantum mechanics arguably the most precise and predictive theory ever developed in human history. Nevertheless, many physicists of that era, understandably, found it hard to believe their own findings and were genuinely concerned about their implications for our understanding of the world. Especially the development of nuclear weapons then brutally forced physicists to realize that these outlandish theories have severe consequences for our macrocosmos. One pivotal and still researched question regarding the impact of quantum physics on our scale is how big a quantum superposition can get. You see, while decoherence scales exponentially with system size, in our general theoretical framework, there is no inherent size limit to a quantum state, provided all sources of decoherence can be shielded off. Moreover, a system in a superposition can be coupled to another system, thereby also bringing it into a superposition. This fact begs the question of whether we can chain larger and larger systems together to eventually bring also macroscopic objects into the state. Part of what this would mean is nicely depicted by the thought experiment of Schrödinger's cat. For this, imagine a magically sealed box, an idealistically isolated system. Inside the box, there's a cat. Next to the cat, a quantum device evolves freely into two potential states. One of these states triggers a lever that would open a poisonous gas cartridge. This is akin to saying the gas is set free when the electron from our double slit experiment goes through, for example, the bottom slit. Yet, as you know by now, the electron goes through both slits simultaneously, and likewise the quantum device evolves as a superposition of both final states. The lever coupled to that device is thus also in a superposition of being pulled and not pulled, causing the cat to be both poisoned and not. So in the end, we seem to have a cat that is alive and dead at the same time. Only by opening the box and thus measuring and decohering the system would we get one of the two states. While Schrödinger came up with this thought experiment to criticize quantum mechanics, it nowadays highlights important questions regarding decoherence and measurement effects, with many proposed theoretical solutions. On the experimental side, scientists were able to build increasingly larger superpositions, or cat states as they are often called now, over the years. The heaviest cat state I know of was created here at ETH Zurich and involves 10 to the 17 atoms, which is roughly the weight of 1 centimeter of human hair, though it is worth noting that the superimposed states were only marginally different. In the end, it's safe to say that quantum superpositions continue to puzzle scientists even 100 years after their discovery. Yet they are no doubt a central element of our universe. Physicist Richard Feynman even called superpositions the only quantum paradigm there is, and all other strange phenomena like entanglement and so on just a logical consequence of them. So by now better understanding this core concept, you are in a great spot to tackle the quantum world with all its weirdness. You could, for example, start by watching my last video about how quantum properties make our TV screens better.